So our final talk this morning is going to be by Robert Pappalardo on revealing Europa's ocean. And let me just say that Bob is a senior research scientist in the planetary science section of the science division of the Jet Propulsion Laboratory in Pasadena, California. That's the other PL, the one on the west coast. His research focuses on processes that have shaped the icy satellites of the outer solar system, especially Europa, and the role of its probable subsurface ocean. He's the Europa study scientist for the development of future Europa mission concepts and a member of the NRC's Space Studies Board. So, Bob.
Good morning. As other speakers have already mentioned, the evidence for a subsurface ocean at Europa is potentially profound. Europa has a surface like no other in the solar system, and its subsurface arguably offers the greatest likelihood for life beyond the Earth in our solar system. Let's take you back to 400 years ago, when, of course, Galileo's observations of the Galilean satellites, including Europa, helped change our sense of place in the cosmos. There was another center of motion out there, which argued for Copernicus's idea. And Galileo, observing over subsequent nights, saw all four Galilean satellites revolving about Jupiter, and using the JPL Solar System simulator, we can reconstruct which ones he saw. And on that first night, it looks as though Io and Europa were grouped together into apparently one little star. The first spacecraft image of Europa was brought to us by the imaging photopolarimeter on the Pioneer 10 spacecraft. It's the only image of Europa from the Pioneer 10 or 11 spacecraft, principally a magnetometer mission. As Torrence reviewed, we knew a little bit about Europa and the other satellites from telescopic observations. We knew that the surface composition included water ice based on spectra. We had some idea of the density, though that information was improved by Pioneer, showing that Europa had a density of about 3, rocky but less than Io, a little bit different from Io. Here's another fun exercise. You can take the new JPL Eyes on the Solar System tool, ride along with the Pioneer spacecraft, and at the right time, on the right date of December 3rd, 1973, look toward Europa and zoom in and see the view that we had at 200 kilometers per pixel at the time of Europa's surface. And it seems just like we're analogous to Galileo, who famously recorded Neptune without knowing it in January 1613. Pioneer also spotted Neptune next to Europa. Through the 70s, as Torrence alluded to, there was the thought that there might be oceans in some of the large satellites of the solar system. And it was John Lewis and his student Guy Consolmagno and then Fraser Finale who proposed from models of composition and radioactive decay that there might be oceans within these satellites. And then in the late 70s and early 80s, tidal heating was discussed as a potential way to maintain oceans. Though Cassin and Peel and Reynolds wrote that convection might kick in and freeze an ocean. That is, if an ice shell is thick enough, then the ice might convect in a solid state like a lava lamp, and that, they thought, would freeze up an ocean. So oceans came and went through this period, and actually it was Steve Squires in a paper with Cassini and Reynolds, who said, well, you know, there might be enough tidal heat if we push the parameters a bit to maintain an ocean within Europa underneath a thin enough shell that it won't convect. And that ocean could be there still today. And that was followed up by Huygens and Stevenson, who used a more sophisticated model in 1989 to say that, yes, it looked like there could be sufficient heat to maintain an ocean beneath a conductive ice shell using a more sophisticated model of tidal heating. So that set the stage, so that earlier work set the stage for Voyager, which saw few large impact craters on the surface, which suggested a very young surface, or perhaps the larger craters were relaxing away, as Mike Malin pointed out in the early 80s along the terminator, along the right-hand edge of that Voyager 2 image at the right. There is mottled terrain, pits and domes along the terminator. Are those tiny craters? And in fact, is the surface very old? The bright lineated planes suggested crustal mobility. It was Schenck and Seifert back in 1980 who looked at the Voyager images and said, you know, there are dark bands that could fit back together with the bright pieces moving back into place like puzzle pieces. But it was nearly a decade before Schenck's then controversial idea of crustal mobility was published. Right around the time Huygens and Stevenson said, you know, it's possible to maintain an ocean. So Voyager 1, of course, had relatively poor resolution at Europa, 20 kilometers per pixel, still 10 times better than Pioneer did, and Voyager 2 had 10 times better than that, 2 kilometers per pixel, but it would remain for Galileo to really greatly increase our knowledge of Europa through imaging and through other techniques. There were, as Torrence alluded to, 12 prime mission close approach flybys by satellites by Galileo, and 3 were usable close Europa flybys. And then there was the Galileo Europa mission, because Europa was turning out to be so exciting that an extended mission would focus on Europa, with 8 close approach flybys of Europa, excuse me, though one of those was gravity only, and 2 of them ended in radiation-induced upsets of the spacecraft. So really with 5 close approach, additional close approach flybys, we were able to learn amazing things about Europa. Of course, it is about the people. I had the pleasure to work with this motley crew as an affiliate of the Galileo imaging team. Mike Belton in front, you can recognize. Let's see, Torrence, you have your hat today. There he is on the right. Clark Chapman in front. Rick Greenberg in the back right. Ron Greeley in the back, organizing the crew a bit. Jim Head in the back left. We've been having fun on Facebook now that I found this photo, tagging away. The first images from Galileo of Europa were only slightly better in geometric resolution than Voyager 2 images. They were 1.6 kilometers per pixel, but the much better camera, a solid state imager, was able to get much higher quality images. And here the surface shown in false color as compiled by Paul Geisler at the time. And what we saw is the right-hand side is littered with some of these pits that we were getting a feel from Voyager. And both Clark Chapman and I looked at the size distributions of these pits and said, you know, they're all kind of the same size. They're all turning out to be several to 10, a little less than 10 kilometers across, which suggested maybe they're not impact craters, maybe they're endogenic features related to internal activity. There were these spots littering the surface, the dark spots, And they also seem to be about the same size. Maybe they're somehow related. Is it related to some sort of internal volcanism or other activity? We found that the surface was brightening with age. Older features were brighter. The idea of non-synchronous rotation had come up from Voyager days, and based on this color composite, Paul Geisler argued for non-synchronous rotation. When we looked at the age of lineaments, there seems to be a rotation of lineaments through time as well, consistent with the icy shell moving independent from the interior, slightly faster than interior, as if lubricated, decoupled from the interior by a subsurface ocean. There were a series of papers published based on some of the first images arguing for crustal mobility, non-synchronous rotation. And this picture from the same sequence was on the cover of the New York Times arguing for crustal mobility. So Schenck and McKinnon, it seemed, were right. The puzzle pieces were fitting back together. This is Europa's surface as it looks stretched out into a global map as we know it today. Very few impact craters. There's one here, this bright one, Pwyll, or Pwch if you're Welsh. There are only about a dozen or so that one can recognize, and from observations of impactors in the Jovian system, we know one should hit every 3 or 4 million years, so you do the calculation, it comes up that Europa's average surface age is about 60 million years. Europa has been repaved since dinosaurs roamed the Earth. We don't know whether that was in a spurt 50 or 60 million years ago, or if it's a continuous process and is ongoing today. But why would Europa die out just 50 or 60 million years ago? In fact, it's probably either an ongoing process or Europa may go through cyclical activity. Predictions of tidal heating as tied to Io suggest that Io is pulling Europa back and forth and increasing its eccentricity and decreasing it again on a time scale of 10 to the 6th years or so. Here's what those ridged planes look like close up. Those lineaments are ridges, not just single ridges, but double ridges crisscrossing the surface. It looks like generations of ridge upon ridge, or sets of ridges, have created those ridged planes. And then there's that model terrain where those pits and spots are. Some show chaotic terrain. Looks a little like hamburger, and that ridged plains has just crumbled in place to form that chaotic terrain. Now, I'm a geologist, and so we were working to understand whether the surface geology told us about an ocean, but it was the magnetometer team. If anyone has discovered an ocean, it was them who, through measurement of an induced magnetic field at Europa, found strong evidence that Europa is acting as a conductor, that Jupiter's external field is inducing a magnetic field in Europa, and that remains the strongest evidence for subsurface ocean at Europa today, that still exists today. And of course, the gravity data, through measurement of the inference of the moment of inertia, tells us that Europa is almost certainly differentiated with an iron core, a rocky mantle, and then an H2O layer, something like 100 kilometers thick. Here's a little illustration from Michael Carroll of Europa in Jupiter's immense magnetosphere, and an illustration of that induced magnetic field at Europa. Recall that Europa is bathed in high energy plasma charged particles with kilo electron volt and mega electron volt energies are slamming into Europa at all times. And while that is a nasty environment and would kill a person in 15 or 20 minutes if exposed to it, it is potentially life nurturing, because when high energy particles slam into H2O, they make H and they make O. And some of those things recombine, and they recombine with the other contaminants on the surface. And they make things like peroxides and formaldehyde and O2. Europa doesn't have much of an atmosphere, a picobar, 10 to the minus 12 bars, but it does have essentially an atmosphere frozen into its surface. There's O2 at that surface. If all of Europa's oxidants could be dumped into its suspected subsurface ocean, then that ocean would be more oxygenated than is Earth's ocean. And that could serve as a fuel for life. We need to understand the processes of whether that material from the surface gets into the ocean and how. Here's what the surface looks like a bit closer up. Sorry, no scale bar here, but again, these spots are something like 7 kilometers across, and ridges are commonly a couple to 5 kilometers across. Some of them are quite bizarre, seeming to bounce across the surface in a cycloidal pattern, not something we're used to seeing on a planetary body. Okay, I'm getting the signal to speed it up a bit. The story of Europa's ridges is interesting because there are many ridge models that have been proposed, and while they're the most ubiquitous feature on the surface, they're the most controversial as well. Is the surface, the ice shell being cut completely through and tidal flexing, opening and closing ridges, a model that has been supported by Rick Greenberg and colleagues? Or are there other models that might involve solid state ice, and it's almost incidental that the ocean is below, enabling large-scale tidal flexing? And one model illustrated is the idea of shear heating, that back and forth motion created by tidal flexing is what is heating a plane in the subsurface and warming that ice and pushing the surface up to form a ridge. And interesting in the sense of the story of Galileo and Europa exploration, these models somewhat led to a schism of, is Europa's ice shell thin or is Europa's ice shell thick? Torrence likes to call it the pizza debate. Is it thin crust or thick crust? And we were working some of the ridge ideas, and Rick Greenberg pointed out that was developing this model, and I pointed out that, well, this model couldn't work if the ice shell, because the ice shell had to be less than about 7 kilometers thick to cut all the way through, and the tidal heating models were suggesting a thicker ice shell, and his response was then the ice shell must be thin. And so he ran with that rather than questioning the model itself. Whereas in a thicker shell model, the ice shell can be pierced down to a ductile layer and pulled apart atop warm, flowing glacial ice. And that's the model illustrated at the bottom right for bands on Europa. We were able to zoom in on some of these wedge-shaped bands that Schenck and McKinnon had originally investigated. And again, the puzzle pieces of each side fit back together perfectly, and the center is striated, analogous to what we see at the mid-ocean ridges at spreading centers on the Earth. And then in the thin debate, it was, is that a top warm ice or is that a top liquid water? Impact craters, as Zibby Turtle and Betsy Pratzo argued, like Puil, argue for an ice shell that's relatively thick, at least 8 kilometers thick, or you wouldn't get a nice crater morphology. And later, Paul Schenck wrote on these multi-ring structures. There are only 2, and he invoked a model that had been developed for Ganymede and Callisto that says if we penetrate through the ice shell to a fluid layer, then the crater fills in, this large crater essentially fills in very rapidly, pulling the brittle ice along inward with it to form these concentric rings. And based on the scale, about 40 kilometers across for the inferred crater, he said, well, then they've penetrated to liquid water at about 20 kilometers depth. Consistent with the tidal heating models. In terms of surface composition, there's a question of what this dark reddish stuff is that we see, and based on infrared spectra, the leading candidates are sulfate salts or sulfuric acid hydrate. And in reality, it's probably a combination of those two. So is Europa's ocean like Epsom salt or battery acid? The answer is more likely that it's like Epsom salt, but that the battery acid is created at the surface by irradiation of the surface. Here are some of those freckles, lenticulae is the Latin for them. When we saw them first, rang a bell with me as what I had heard about that Reynolds and Casson model way back when, that convection may have kicked in the ice shell, and perhaps what we're seeing is the tops of diapirs, warm ice blobs that have risen up through Europa's ice shell, again implying that it would be more than 20 or so kilometers thick. And the bottom is showing a model by Amy Barr of that warm flowing ice, all the red being only about 30 Celsius below zero in terms of the temperature. Warm ice, even though the surface is 100 Kelvin, that warm convexing ice would be 240 or so Kelvin. An illustration of the lava lamp-like model of Europa's subsurface convection. Some of the most fascinating terrain, our chair's starting to get up. Some of the most fascinating terrain is this chaotic terrain. And in the thinner, thick model of the issue was, has Europa's ice shell melted out completely, or have blobs of warm ice risen and moved to the blocks above, like in a mosh pit? And recently, Brittany Schmidt has suggested an interesting hybrid model, that chaos may form above a melt zone in a thick ice shell, that essentially we're looking at areas that used to have lakes beneath them the size of one of the U.S. Great Lakes, and that some of these regions may still have lakes beneath them today. And so the discussion continues as to whether we're actually looking at floating icebergs. And here, just for you, Torrence, the Titanic is about 270 meters from stem to stern. So Europa may have the ingredients for life. In terms of water, more than 2 times all of the Earth's oceans, in terms of the essential elements from its formation and from impacts bringing carbon and other elements. It may have chemical energy from above, oxidants created at the surface by irradiation, and potentially energy from below. If the mantle is warm, if it is tidally heated, then there could be black smoker-like activity pouring reductants into the base of the ocean. And it's probably a relatively stable environment, somewhat variable, but simmering for 4 billion years. So that leads to basic questions about the ocean, its existence, its extent, its salinity, about the ice shell, the existence and nature of water within and beneath, the nature of the surface ice-ocean exchange, composition, the distribution and chemistry of key compounds, the links to ocean composition, and the geology. What are the characteristics, formation of surface features, including sites of recent or current activity? And these all relate to that overarching theme of Europa's potential habitability. The history of trying to develop the next mission to explore Europa from the late 1990s could be a talk in itself, but I'll simply say that the latest iteration is a very feasible one that could cost about $2 billion, short of launch vehicle, would address these ocean ice shell composition geology objectives, and could have a reconnaissance camera as well to set the stage for a future lander. It would do several dozen close flybys of Europa to understand the nature of its ocean and understand its habitability, potential habitability. And just to finish, there are important fundamental questions remaining to answer in our solar system, especially with regard to its potential for life beyond Earth, its origins and its commonness. It was 400 years ago Galileo's observations of the Galilean satellites changed the human perspective on our place in the universe, and it's fascinating to think that one of those worlds could in the future change it again. Thank you very much.
Thank you, Bob. It's tough to explore and talk about an entire world in 20 minutes. I'll tell you what, why don't we go ahead and assemble the panel, and so let you take a seat, Torrence and Arturo, if you can come on up, and if you have a question for Bob, why don't you try to get first in line? Okay. But we will see. Please go ahead.
Okay. I don't see speaker. Oh.
It's hard to see around
Robert,
the columns.
You mentioned about some kind of the variations in the mutual position of the, say, Europa and Io, you know, and in addition to the regular change. So are these deviations mostly just produced by the Laplace resonance, I mean within Laplace resonance, or it's some kind of additional mechanism exist? And how deep such fluctuations are? Whether their influence on the depth of the ocean or only on the temperature?
Yeah. So the idea that's been developed is that by Io heating up, it could heat to the extent that its ability to dissipate heat actually decreases. And to conserve angular momentum, that will actually end up changing slightly its orbital eccentricity. And it will drag Europa along as it does so. And recent models have suggested Europa's ice shell thickness could fluctuate from something like 10 or 15 kilometers up to something like 30 kilometers. So it's possible Europa may have even experienced a thin shell-like history and a thick shell-like history, and that may vary on something like a 10 to the 6 year cycle. About 10 to the 6 years is in the models, but the models can be tuned. There are a lot of parameters, so.
Yes.
Thank you, John Sarkisian from CSIRO Australia. This is a question for Torrence. We've heard about how the spacecraft get to the planets and we're able to image them and so on, but very little's been said about how that information's actually returned. Torrence, would you like to say a few words about the Deep Space Network involvement in those outer planet missions?
Sure. Communications is obviously a critical element in all of these things, and it often operates beneath everybody's visibility level. It's just something that happens. As a scientist, I just regard that as part of the magic, because I can't figure out how we get all those bits back from out there. And I know, John, that I talked with you the other day walking over, and then I realized reading your bio that you were one of the people who were at the Parkes facility in Australia that helped bail us out when our communications system became a little flaky on Galileo. And it's a marvelous story in itself, how these communication systems, codes, cooperation amongst the various institutions and radio tracking facilities around the world go. You're quite right to bring that up.
Heidi.
This is for Torrence. We'll hear from Chaz tomorrow how most about the exoplanets, and the Kepler spacecraft is showing that many thousands of candidates are Uranus and Neptune-sized bodies, and yet the only mission that has ever gone to an ice giant was launched before I even graduated from high school, and now I got gray hair. And you've already pointed out that we're looking at a radio dark outer solar system now. What's your thoughts from a historical perspective of how that got lost from the Jupiter orbiter and the Cassini-Saturn orbiter, and why did it get lost that we don't have an outer planet orbiter? What happened, and what's the lesson learned so we can fix it?
I think the discussions yesterday illustrated how cyclical the funding for this entire enterprise is, not just outer planet exploration. It's not something that's taken for granted at the political level. It's something that we have to continually make the arguments for. I would just remark from a historical point of view, we were well served by jumping on top of the Grand Tour alignment. I mean, that for the outer planet exploration, because that actually got us some data in remarkably short times. And it's not going to happen again for a while unless we get warp drive. So I think we have not lost the drive to do these things, but we're still struggling with the generational nature of how long it takes to do them. I agree with you there.
Thanks, Jennifer Tessie, Princeton University. That was a great question. Of course, it's interesting to note that the generational moment corresponds to when a lot of attention has been placed on Mars, as opposed to how long it takes for satellites to get to the outer system. I was really struck by the presentations, which look like we're talking about planets and moons and institutions, but we're also really talking about some important relationships that made those systems work. And I'm struck by the number of times we've seen, that Torrence has participated in several generations of missions, or Paul Schenk's name coming up over and over again, or these strong relationships between NASA and ESA that enabled something like Cassini-Huygens to be the success that it is. And I think I, like many people in this room, have been very dismayed or distressed at the cancellations of some of the larger scale international collaborations between NASA and ESA, specifically whether it's ExoMars or the potential of a joint mission to Jupiter's moons. And I'm wondering if the three of you could speak from your experience as to what are the parameters for success for building the kinds of strong relationships, whether it's across institutions or across missions or across continents, that enable these kinds of missions to go forward.
Let me just make a preliminary comment on that and then ask my colleagues, is that I have frequently tried to make the point when speaking to media that we got the wrong name on our program by allowing it to be called unmanned or robotic. It is profoundly human, and the crew of these spacecraft are right here on Earth and in the command center. And now with social media and other things, we can bring the rest of the population of the world together with that. That's been an evolving picture. And that's true in the science community, but there's a broader context to it.
In planning these next missions and looking toward future missions, there was a meeting several years ago working with many of the same members of the science definition team we've been working with for many years, when came to the realization it's about the journey, that we have to be enjoying ourselves along the way and working with good people who have that very long-term vision. And I think those who are dedicated to that future exploration work so well together because they have that long-term common goal. And so I'll stop there.
I have not much to add to what I said, but I think, first of all, you have to consider that space science is not a scientific discipline. It's a complex, a set of very different scientific disciplines, and so there are always competition and cooperation aspects which play a role in this field. Secondly, even given the scientific disciplines that we call space science is not only science. They need technological means, rockets, spacecraft, communication networks, political decisions, huge amounts of money. So it's not only science, and science is not even the most important driving force behind space science. Third, the most challenging and important scientific mission in space have to be done in collaboration. Big collaborations, small collaborations. Just having a launcher is a collaboration. Having the deep space network for ESA is essential. If you want to go to the outer solar system, you need an RTG generation. You cannot have this in Europe. So that demands, in any case, some kind of collaboration. And all of this implies scientific personal relationships, but also complex political and economical negotiations. So the situation is always very fluid. The difference in the budget system in Europe and in NASA has been the major stumbling blocks in several cases, and was a source of not less important controversies in some cases.
Yeah, I would note further that Professor Russo pointed out the tensions in the relationships between ESA and NASA particularly. What amazed me was that the relationships survived. I wasn't certain when we started talking on Cassini whether my European colleagues would even talk to us after what the United States had done with respect to the Ulysses program. And it was personal relationships that allowed people to say, hey, you know, there's a bigger picture here. We have to work together on this. We're not going to be able to accomplish these things.
So let's take one final question.
Let me pick up on that theme, actually, because that's my question, and ask the striking difference between what Professor Russo described and what Bob has recently experienced in the construction of an international program for outer planet exploration. It seems now, as a result, we're in a phase where U.S. and Europe are going apart and planning their programs independently, not just the outer planets, but at Mars too, it seems, as we heard earlier. What's the impact of the current situation on this with respect to the future outer planet exploration?
I'll start with the Europa Ganymede discussion, and maybe others can pick up. But we've certainly, so we were working together as one wonderful group when the U.S. said, okay, we're not doing Europa, and Europe said, well, we are doing this Ganymede mission, which has become JUICE. Again, the personal relationships continue. We certainly want to work together with our colleagues in Europe to explore the Jupiter system. There will be U.S. participation in the JUICE mission. And we're doing all we can on our side to try to keep alive that vision and resurrect a Europa mission for the exploration of Europa and the Jupiter system, including Ganymede, as a whole. But without the U.S. participation, we will continue to have tantalizing hints of what Europa is like, but we won't have answers. And my fear is that 50 years from now, when we do explore Europa and we get a lander to the surface and we sample that stuff, my fear is we'll say, why didn't we do this 50 years ago? Because it could be that important.
All right, let's thank our panel once more. And you may blame the moderator for cutting out 7 minutes of your lunch.
No, quite the contrary. Thank you, Ralph. You did a fine job, and thanks to the panel for such a stimulating discussion. A couple of quick announcements before we break. If you haven't already done so, please take the opportunity to avail yourself of the oral history recording crew. They're not down at this end today. They're down at this end. When you go out, it'll be to your left. We've got a lot of experience and talent in this room, and let's share that as much as we can with the public and with the next generation. We will be reconvening at 1 o'clock, so keep an eye on the clock. 7 minutes won't hurt us, but we do need to be back at 1. And lastly, please remember the admonition to take a buddy to lunch. Again, the advantage of having us all here physically in one place is the interpersonal interaction, and lunchtime's a great time for that. So without further ado, see you back at 1.